My name is M. Sadman Astar and ID is 2000213444. Today we will be discussing on the rectangular waveguide. We will start from the basic definitions, move through the mathematical foundations and mode structures. Rectangular waveguide. Rectangular waveguides are one of the earliest types of transmission lines used to transport microwave signals, and they are still used for many applications. Large variety of components such as couplers, detectors, isolators, attenuators, and sorted lines are commercially available for various standard waveguide bands from 1 to 220 GHz. The hollow rectangular waveguide can propagate T transverse electric and transverse magnetic both, but it cannot propagate transverse electromagnetic waves since only one conductor is present. Now we will see TM and TE modes of a rectangular waveguide have cutoff frequencies below which propagation is not possible, similar to the TM and TE modes of the parallel plate waveguide. We will first discussing the TE modes. For TE modes, it is assumed that the guide is filled with a material of permittivity epsilon and permeability of mu. It is a standard convention to have the largest side of the waveguide along the x-axis so that A is greater than B, and here it is a perfectly conductive body. We know that transverse electric waveguides modes are characterized by a field with where Ez is equal to 0 and there remains a component of Hz, and these satisfy the reduced wave equation that we derived earlier. And here is the reduced wave equation: del square del x square plus del square del y square plus kc square. Hz is a function of xy. Here the wave is propagating through z direction, and here is the kc, which is the cutoff wave number defined as root over k square minus beta square. Now for the partial differential equation, it can be solved by the method of separation variables. For this, we will let this function hz of xy in terms of x and y variable. Now we will plug in these values of this equation into equation 1. Then we will get this equation, which is 1 by x d squared dx square of x plus 1 by y d square dy square of y plus kc square is equal to 0. Now, by the usual separation of variables of arguments, each of the terms in this equation must be equal to a constant, and thus we can write this equation in such manner. Now we will find the general solution, and the general solution can be written in terms of sine and cosine function, and we get the general solution of hz of xy as a cos kx plus b sin kx into c cos ky plus a d sin ky. Now we will be applying the boundary conditions. As we can see that at y is equal to 0 and y is equal to b, ex component is a 0. Again, at x is equal to 0 and x is equal to a, the ey component will be 0. And we will be using these boundary conditions. Now we find the ex and ey from hz. We get the ex and ey equation from the general solution of transverse electric wave equations, which were derived previously. Now we will plug in the values of hz in the corresponding equations. Then the equation will look like this: ex, ey. Now, after applying the boundary condition and simplifying the calculation, we get that d is equal to 0, d is equal to 0, and ky will be n pi by b. Again, applying the boundary conditions, we will get b is equal to 0, and kx will be m pi by b, where m and n will contain discrete integer values starting from 0 and it goes on. And thus we get the final solution for hz, and this is hz function of xyz is equal to a into cos m pi x by a into cos n pi y by b into to the power minus j beta z. That z denotes the wave is propagating in the z direction. Now the transverse field components of the transverse electric mode can be found by plugging in all the values that we have found till now, like putting the values of ky, kx. We get the simplified and final equation of ex, ey, hx and hy, and these equations were derived previously, and we found those equations from the general solution of transverse electric wave. We just plug in the values here and get the final equations. We know that beta is the propagation constant, and beta is defined as root over k square minus kc square, and kc consists of kc square is equal to root over kx square plus ky square, and we got the values of kx and ky beforehand. Here the values of kx and ky are ky and kx. Now as kc square is equal to kx square plus ky square, we can plug in the value of kc square in this equation, and finally we get this equation. And when k is greater than kc, the equation turns into like this. Each mode, each combination of m and n has a cutoff frequency, which can be denoted as fcmn, is denoted as kc by 2 pi root over mu epsilon. Now we plug in the value of kc here, and we get this finalized equation. The mode with the lowest cutoff frequency is called the dominant mode. Because we have assumed that a is greater than b, the lowest cutoff frequency occurs for the TE10 mode, where m is equal to 1, n is equal to 0. Here is the lowest cutoff frequency, FC10. Thus, the TE10 mode is the dominant transverse electromagnetic mode. We will see the overall dominant mode of the rectangular waveguide. We can observe that the field expression for E and H in previous equations are all 0 if both m and n are 0. Here we can see. At a given frequency f, only those modes having f is greater than fc will propagate. Where the frequency will be greater than the cutoff frequency, these modes of waves will propagate, and modes with containing f which is less than fc will lead to imaginary beta, meaning that the field component will decay exponentially away from the source of excitation. Such modes are referred to as cutoff modes or evanescent modes. If more than one mode is propagating, the waveguide is said to be overmoded. We will calculate these equations of f01, fc11, fc20 by simply putting the values of m and n to these equations that we have derived earlier. Like for fc01, m is 0, n is 1, and if we plug in the value of m0, m is equal to 0, n is equal to n, here we get the equation of f01. Similarly, f11, we put the values of m is equal to 1 and n is equal to 1. Again for fc20, m is equal to 2 and n is equal to 0. We get these equations. Now we will be discussing a bit for TE10 mode. Here m is equal to 1, n is equal to 0. After plugging in the values of m and n and kx and ky in the equations, field components of the field components equation, we get this simplified equation. And here we can see a field pattern of the dominant TE10 mode. The dominant TE10 mode, where m is equal to 1, n is equal to 0, shows one half sign variation across A and uniform along B. Its electric field peaks at the center, here we can see, and goes to 0 at the board walls, like this. We typically design to operate above its cutoff but below the next cutoff to ensure single mode propagation. Now we'll be discussing on power flow analysis. In a waveguide, power flow refers to the amount of electromagnetic energy that travels down the waveguide per second. We calculate this using the Poynting vector, which tells us how much energy is flowing at any point in space. Poynting vector is denoted as S is equal to cross product of E and H. Only the transverse electric and transverse magnetic modes carry power. In rectangular waveguides, only the transverse TE and TM modes can carry energy, and the TEM mode does not exist here. So in power flow analysis, we will not consider the case of TEM mode. The generalized idea for power flow analysis in a transmission line was like this, that we calculated the voltage and the current first. The voltage equation was given as V is equal to Vm cos omega t plus theta V. In phasor form, it can be written as Vm theta angle theta, and I equation was Im into cos omega t plus theta I, and in phasor form it was written as Im angle theta. And we know the power equation is P is equal to Vi, and we plug in the values of V and I here, and we get this equation, which is Vm Im cos omega t plus theta V into cos omega t plus theta I. Now we use the formula of 2 into cos A cos B, which is equal to cos A plus B plus cos A minus B, and using this equation we get the final equation of power Vm Im by 2 into cos theta V minus theta I plus cos omega 2 omega t plus theta V plus theta I. And this is the power equation. Now to get the average power equation, we integrate the power from 0 to t and divide it by the total time period to get the average power, and here is the final equation. This is our average power. And for power flow analysis, we also need to take the conjugate of current, and that is denoted as Im angle of minus theta. We find the Vi conjugate term, which is Vm Im angle theta V minus theta I, and in terms of sine and cos, it can be written like this. And if we take the real part of this equation, which is half of real part of v into I conjugate, we eventually end up with this equation. And this equation was used to do the power flow analysis in generalized form or in transmission line. We will apply the similar concept for electromagnetic wave. So we will be using the radial Poynting vector that we discussed earlier, which is the cross product of E and H, and take the real part of it to get the average power. Now we will plug in the value of E and H conjugate. E and H were found previously here, and applying this equation of E and H and get the cross product of it, then we will do the surface integral along x and y direction of this radial Poynting vector, and taking the real part of this whole equation will give us the average power. And eventually, after doing all the calculation and simplification, we will get this equation. We will end up with this equation, which is omega into mu a cube into b beta a square by 4 pi square. And thus we will be doing the power flow analysis for electromagnetic wave. Now we are left with finding out some parameters. One is ZTE. ZTE is the wave impedance that relates the transverse electric and transverse magnetic fields. ZT is denoted as the ratio of Ex and Hy, which can be again written as minus into the proportion of Ey and Hx, and can be eventually written as k into eta divided by beta, where beta is the propagation constant and Zt is real when beta is real, which denotes a propagating mode, and Zt becomes imaginary when beta is imaginary, which denotes a cutoff mode. Again, the guide wavelength is defined as the distance between two equal phase planes along the waveguide, and the guide wavelength is denoted as lambda g and is equal to 2 pi by beta. It basically denotes the distance between two equal phase planes along the waveguide. Now we will be discussing another two parameters, which is phase velocity and group velocity. The phase velocity is denoted by the ratio of angular frequency and propagation constant Phi is equal to omega by beta, and above the cutoff the guide is dispersive. And the group velocity is defined as the ratio of change in angular frequency divided by the ratio the group velocity is defined as the ratio of change in angular frequency divided by the change in propagation constant. And these were the remaining parameters that were to be discussed from T. Now we will be discussing on TM modes of rectangular waveguide. The structure is the same as before. Here it is assumed that the guide is filled with a material of permittivity epsilon and permeability of mu, and it is a standard convention to have the longer side of the waveguide along the x-axis, and so A is greater than B. And here it is a perfectly conductive body, and also in this scenario the wave is propagating towards positive z direction. We know in TM modes the magnetic field along the z component h of z is equal to 0, and there remains a component of Ez, and this Ez component must satisfy the reduced wave equation. This reduced wave equation was found previously, it was derived previously, and here we can see the cutoff wave number is also defined, kc square is equal to k square minus beta square. Now this is a partial differential equation, which is denoted as equation 1. It can be solved by the method of separation of variables procedure, and solving this partial differential equation we get the general solution in terms of cos and sine function, and the general solution is Ezxy is equal to a cos kx into x plus b sin kx into x into c cos ky into y plus d sin ky into y, and this is the general solution. Now we will apply the boundary condition and boundary condition to this general solution. Here in the structure we can see at x is equal to 0 and a, the Ez will be 0, also in y is equal to 0 and b, Ez component will be 0. Now we will be putting these two boundary condition into the general solution, and we will end up getting a will be 0 and kx will be m pi by a, where m will be integer number starting from 1 and it will go on. We also end up with the decision that c will be 0 and ky will be n pi by b, for n will be one integer number starting from 1 and it will go on. Now after simplifying and putting the values of kx and ky to the general equation Ez, we will get the final equation of Ez, which is bmn into sin m pi x by a into sin n pi y by b into e to the power minus j beta z. Here the z denotes the wave is propagating along the z direction. Here the bmn is an arbitrary amplitude constant. Now the transverse field components of the TM mode can be computed from the general solution of the TM wave, which were proved and derived previously in the previous sections. And from those general solution we get the equation for Ex, Ey, Hx and Hy. and we put the value of kx and ky in these equations, and eventually we end up with the final and simplified form of this equation. As we have also seen in the previous case of TE modes, that the propagation constant beta is defined as root over k square minus kc square, which can be further enhanced in the up to this equation, putting the values of kc, and kc consists of kc square is equal to kx square plus ky square, and then we put the values of kx and ky that we got here, and eventually we ended up with this equation, and that was for the case of TE modes. And also the cutoff frequencies for the TM modes are also same as those of the TE modes. The guided wave length and phase velocity for TM modes are also the same as those for the TE modes. So this equation is also valid for TM modes. We also observe that the field expression for E and H are identically 0 if either M or N is a 0. I mean, this equation will turn into 0 if either M or N turns to 0. Thus, there is no TM00, TM01, TM10 mode. And hence, the lowest order TM mode to propagate is TM11 mode, which have the heavy cutoff frequency of FC11. And this cutoff frequency is defined as previously C11 is equal to 1 by 2 pi root over mu epsilon into root over pi by a whole square plus pi by b whole square. We will find these equations same as previously. Here m is 1 and n is 1. We just simply put the value of m is equal to 1 and n is equal to 1 here, and eventually we'll end up in this equation. Now we will also discuss the other frequency components such as FC21, FC12. For FC21, m is 2 and n is 1, and putting those values of m is equal to 2 and n is equal to 1 in this equation, we finally end up with this final equation, and the same goes for FC12. And now we can see here a sequence graph. This sequence graph denotes the TM modes in a standard X-band rectangular waveguide. Here we can see between FC11 and FC21 band, the TM11 mode only exists, and here the cutoff frequency is approximately 16.2 GHz. Then we go to the next section. Between FC21 and FC12 mode, there only exists TM11 and TM21 mode, and the cutoff frequency in this range is 19.8 GHz. And then we go to the next section, which is above FC12, and for FC12 and above this range, all the components like TM11, TM21 and TM12 exist, and the cutoff frequency here in this range is approximately 32.5 GHz. And this actual sequence of FC depends on B by A component or B by A term. Now we will be discussing on some other parameters. First, we will talk about the ZTM. ZTM is the wave impedance. The wave impedance relates the transverse electric and magnetic fields for TM mode. The wave impedance can be written as the ratio of Ex by Hy. For this scenario, where the wave is propagating along the Z direction, it can also be written as minus Ey by Hx. It can also be written as beta into eta divided by k, where beta is the propagation constant and k is the cutoff wave number. Now we will be talking about the lambda c, which is known as the cutoff wavelength. It is basically the longest free space wavelength that can still just barely propagate. And when lambda becomes greater than lambda c, the mode becomes evanescent and cannot carry power. The lambda c equation is 2 pi divided by kc. Kc is the cutoff wave number. Now we will be discussing on lambda g, which is guide wavelength. The guide wavelength is the wavelength inside the waveguide, which denotes the distance along z over which the phase advances by 2 pi. And the equation for lambda g is 2 pi by beta. Here there is an intuition that when f approaches to fc or cutoff frequency, then beta tends to 0, and for this scenario, the lambda g approaches to infinity, and this scenario denotes the wave stretches out along the guide. And there is another term left, which is Vp or phase velocity. Phase velocity is the speed at which the constant phase point travels along the guide, and the formula for Vp is omega by beta. And these were the parameters which were left for discussion, and this is the overall discussion on the TM modes of waveguide. Previously I discussed on the TE modes of a rectangular waveguide, and this concludes the overall discussion on the rectangular waveguide.